In this video, we're going to discuss something called the Maxwell Relations, which is really one of the crowning achievements, I guess, of 1800s thermodynamics, because it relates a lot of these quantities to one another using these differential relationships. I realize that probably isn't what you wanted to hear, but let's look through this and I'll show you what some of the things you can learn from the Maxwell Relations are. Now, before I jump into the Maxwell Relations, I want to first establish what is the principle of the thing that we're doing. All right, the principle is that we have functions that are implicitly functions of a couple of variables. And if I were to write down the total differential of a function like this, I know that this would be df dx at constant y dx plus the partial of f with respect to y at constant x dy. And that would represent the total differential for my function df. But I also know that in general, if I've got a functional form for this, that the second derivative of this function, and I'll say the second mixed derivative, has the following relationship, that the second derivative with respect to x and then y is simply equal to the second derivative with respect to y and then x. So that means that I can take these, these functional forms here, and we've already seen that we can use that to test if something is an exact derivative. But now I want to do something slightly different. I'm going to say that this derivative here, this first derivative, is some function a of x and y, and this second derivative is some function b of x and y. So now if I were to take, shall we say, the d dx of the derivative of f with respect to y at constant x, okay, d dx of that is technically going to give me d squared f dx dy. But if I use my value for here from here, that's just b of x and y. So this is equal to the derivative with respect to x of b of x and y. Or I could write that as the derivative with respect to derivative of b with respect to x, and implicitly with y as a constant. All right. Now I could have started over here and said, the derivative with respect to y of df dx at constant y is something that represents the second derivative of f with respect to y and then x. And I know that that's equal to this. So these two things are equal. But now I can write this as the derivative of y of df dx dy, which is just a of x and y. So this is really equal to d dy of a of x and y. Or, in other words, it is dA dy at constant x. Okay, partial. But since these two things are equal to one another, these two things are equal to one another, then these two things are equal to one another. So I could actually put a little bit of a box around this. And this is a way of not only testing if this is an exact differential, but it's also a relationship between these results, because when I look at the results that I have for thermodynamic potentials, I know that in fact these partial derivatives with something held constant are equal to one of the thermodynamic physical properties. So now I have new relationships that I can derive between those thermodynamic physical properties. So let's see what this looks like. All right, what I want to do is start with the internal energy. So in internal energy, I would have, for example, a function that is a natural function of S and of V. And I know that when I write down this, its total differential, it's going to be du ds at constant v ds plus du dv at constant s dv. But I also know that this particular function is t ds minus p dv. So I can immediately associate t with this derivative and p with this derivative. But now let's suppose I want to invoke this second derivative, and what I'm looking at is the second derivative of u with respect to both s and v. I shouldn't put a comma there, sorry. All right, so I'm interested in this and its opposite, the cross derivative that it's related to. Well, I'll go ahead and write it out. d squared u dv ds. All right, but now that I have, this is basically my a and this is my b. Now that I have those, a was derived from taking the derivative with respect to s, so now I have to take the derivative of this dt with respect to the other coordinate, which is v. And it's going to occur at constant s. Similarly, on this side, I'm going to take, this was formed from a derivative with respect to volume, so now I need to take the derivative with respect to entropy. And this is going to take place at constant volume. Now I can't forget the minus sign here, so I'm going to put the minus sign out in front. So what I have now is a new relationship that relates these things. And this new relationship is giving me new information, if you will, about these physical properties in thermodynamics and how they might be related to one another. I'll note that in particular, it's giving us relationships that will allow us to express certain derivatives that involve the entropy with derivatives that involve other thermodynamic properties. So it may in fact be useful for us in terms of uncovering ways of calculating these derivatives for particular quantities that involve a derivative with respect to an entropy or something like that. All right, so how does this work in practice? Well, let's look at each of the different thermodynamic potentials. So I've got dH, dA, and dG. Now, when I write these things down, dH, and I'll write these expressions explicitly, dH, H is a function of S and P, so it will be dH ds at constant P ds plus dH dP at constant S dP. But I also know that this quantity is T and this quantity is positive V. So now when I want to get the mixed derivatives, how do I construct those? Well, here's a little bit of a prescription for doing that. All right, I'm going to take the derivative of this quantity that's represented by this partial derivative, and I'm going to do it with respect to the variable that was held constant here. And then the quantity that I'll hold constant is the thing that appears over here in the differential. So this will be the constant. It will then be equal to this quantity, the derivative taken with respect to the thing that was held constant here, with this, the differential part, being the quantity held constant. So now my new relationship here is going to relate a partial derivative of temperature with respect to pressure at constant entropy equal to the partial derivative of volume with respect to entropy at constant pressure. So this again gives me a relationship that could be used. All right, now I'll let you go through these others more carefully. I'll write them out for you so that you can see what these look like. But the total differential for the Helmholtz energy is simply going to be this expression, but I know that dA dt is minus S, dA dV is minus V. Since they're both minus, I'm going to end up with no minuses in my partial derivatives. Okay, but I will have a partial derivative of S with respect to, and I left out the V down here and the T down here. So it'll be ds dV, all right, at constant temperature is equal to dV dt at constant, what did I do here? This should be AP. So it's dP dt at constant volume. All right, so this will be another one of these special relationships. Sorry about the hesitance there. All right, now finally for Gibbs energy, I'll have the Gibbs partial, this is again a function of pressure and temperature. So dg dt at constant pressure dt plus dg dp at constant temperature dp. And I know that this one is going to be minus s and this one is going to be plus v. So in this case, I'll have the following cross derivatives for my differential relationship. I'll have a negative ds dp at constant temperature is equal to a positive dv dt at constant pressure. All right, so this will round out the last of these relations. All right, so these four relationships are together the things that we call the Maxwell relations.